Welcome to the GoldSim webinar for the, let's see, this is April 2025. And today I'll be talking about modeling reference evapotranspiration using GoldSim following the FAO Drainage and Irrigation paper number 56. And if you would like to learn more about it after this presentation, just Google that document, and you'll find there is a PDF that includes the full description of the methodology, and that is what this GoldSim implementation adheres to. And so what I'll do today is first introduce the let's see, moving to the next page. The first thing I'm going to do is introduce the concepts within the reference ETo calculations, in particular what's called the Penman-Monteith method, give some background on that, and then talk about the data requirements for the model, followed by a live demonstration. All right, so let's get started. Oh, also during the presentation, if you have any questions, please feel free to type them into the chat and I'll be happy to answer as we go. So first, we need to talk about understanding what is evapotranspiration, otherwise known as ET. It is a major component of any water balance that you might be doing, whether that is for an agricultural application or also for natural watersheds. Perhaps you're looking at modeling the rainfall runoff process and you have a heavily vegetated watershed that makes up the catchment to the area that's contributing to runoff. This methodology would definitely be applicable for either one of those cases. So it essentially reflects all of the water loss from the soil and the plants. And you can see from this diagram that it's kind of representing that part of the process. We have evaporation from the soil surface, and then we also have transpiration from the essentially the leaves of the plant matter. And then in your whole water balance, you might have irrigation, you might not. So that could be an optional thing there. But you have rainfall that contributes, and then you might also have some subsurface inflow. Anyway, the parts of this water balance that are difficult or probably impossible to measure mainly would be ET, deep percolation, and capillary rise. Those would be the really hard ones to get to. And so what the Penman-Monteith equation allows us to do is estimate ET, and that allows us to do a much better job of doing this water balance because the capillary rise component would be demanded from the ET rate. Okay, so why do we need reference ET, in particular the thing that's called ET with a little 0 next to it or O next to it, ETO? Why do we need reference ET? So what's happening here is we're talking about an equation that is for calculating the essentially the resistance of both the soil and the plants to be allowing the water vapor to go into the atmosphere. And there's two components of that. There's aerodynamic resistance, noted in the figure 7 below as RA, and that's really driven by wind, and that's kind of like blowing it away. There's also other things that come into play there as well, temperature, humidity, and so forth, mainly airflow. And then the other one is the bulk surface resistance, which is the resistance of the water vapor to be leaving the soil and the plant matter. And the figure at the top, figure 1, is showing more detail on as far as at the leaf itself, where the water vapor would be leaving the little cells within the leaves. And so there's a resistance there, combined soil and leaf water vapor leaving, that is called surface resistance. The combination of those two items are what contributes to this reference ET. And because those two components are difficult to measure, the great thing about having this reference ET is that it was done for a hypothetical situation that allows us to standardize the rate and estimate that rate as a constant. So essentially allowing us to then go to other places where there might be variable, there's different climate, there's different vegetation, the different soils, and we can derive or estimate the reference ET by essentially looking at this the standard and then changing it. Sorry about that. That was my dog barking. There's a lawnmower outside, so we might hear some more of that. Okay. So anyway, by isolating this ET for a standard hypothetical situation, we're able to then calculate ET or estimate ET for areas where those characteristics are varied from the standard. So let's talk a little bit about the standard. So the standard is on green grass that has a uniform height of 0.12 meters. So it's like really exact in this kind of lab type environment. And also there's no stress. It's actively growing and well watered. So under those conditions, then they're able to, measure exactly what those RS and the RA components are, those resistance components. And you can think of when it says resistance, think of it like you would in an electrical engineering scenario, similar type of phenomena going on. Essentially, the resistance of the flow. Instead of electrical flow, we're talking about flow of water vapor from one pressure to another out into the atmosphere. Okay, so in this functionality, then our aerodynamic resistance is in this model a function of the wind speed, and which we'll get into. So let's see. Yeah, so we use this ET as a basis then for estimating ET for other areas by applying what's called a crop coefficient. And we can go further into that, but this is not really the purpose of this presentation. This would be for down the road, but essentially we would go from reference evapotranspiration to evapotranspiration of your site by applying this KC factor, crop coefficient. And so now you might be wondering, well, what about just water surface, like a lake evaporation? Well, it turns out, and you can read about it in the paper, that this methodology is actually applicable also for estimating evaporation from any wet surface, including a lake. And in the document, I just cut out a snippet of a table. It's table 12 in the document. And what it does is it goes through all these different crops and tells you what are the KC values for different periods of the growing season, mainly for right after planting when you have an initial period, and then there's a mid period and an end, and there's transitions between, and you end up coming up with these curves of various evapotranspiration rates during the whole irrigation season. But when we're talking about a lake, it might just be a constant if it's a shallow lake. The thing is with the deep lake, deep water, is that it has more capacity to have storing energy, storing heat. And so you might have a difference in the spring and summer than you would in the fall and winter. And so you just want to keep that in mind. There are notes about it in the table, as you can see there, under where it shows open water is greater than 5 meters. But anyway, I'm bringing this up just because this methodology can be used for calculating lake evaporation. And then there's model inputs. There's some weather data that you'll need for this model. I'll talk about it when we get into the model itself. So I'm going to let me close this, and then okay. So what I'm going to do is, let's see, I'll start first with the basics. Okay, so this is a model that I will be updating on our website. It's currently on our website. I just need to move some things around here. But I've updated it a little bit while preparing for this presentation, just to make things a little bit more clear. And so just you can await that. Once I post the recording of this webinar, I will also update the model. Okay, so the input parameters for this model. Well, this is the main model. When you open it, this is what you see. Essentially, we have some input parameters. We have all the calculations for the meteorological processes and information. And then from that, we're able to derive the reference ET. And then in this model, I also do a quick validation. I obtained some monthly reference evapotranspiration rates in the Salt Lake City, Utah area. And then I just use that for, validating the model. I didn't really do very much calibration because all these input parameters are also local for that area. But let me go through the model itself. So on the input side, this is the important thing. We have site data and we have weather data. And the site data makes up, it's the latitude. That's what's important for calculating, for example, the radiation coming in from space. It's dependent on, the location there. There's also an input here for whether you're in the north or the south hemisphere. And I should probably look into that, because I think if we just put a negative latitude, I think that would put us down there anyway. But anyway, make sure you change that if you're in the southern hemisphere. I will check that before I post this model, that might not be necessary to have both of those. But anyway, Z is the elevation of the site above sea level. And then finally, there's this effective soil depth, which is it's not something you really need to change. It might seem like it's really important, but really what this is for is to determine the depth of the soil where temperatures can be affected. So for example, once you get down below a certain depth, then the heat of the sun and everything is going to be minimal. And so we're just trying to capture that depth where it can be affected that way. And it should also be noted that when you're running a one-day time step, the value is going to be around between 0.1 and 0.2. But if you go to a monthly time step, it would need to be larger to account for the impact of having a longer time duration of heat. But also, I need to make note that this particular parameter affects a variable that we might not even use. For a daily time step, it goes into a factor that has very little impact on the model. So I wouldn't really worry about this one too much. Okay, so I didn't want to spend too much time on that minimal thing, but I just wanted to make note of that. Also, the weather data. So this is the important part right here, all the weather data. So there's 4 main inputs. We need sunshine duration, and then we need temperature. In this case, we have daily Tmax, daily maximum, daily minimum temperatures. These are typically go together when you're looking up temperature data at a location. If you cannot get Tmax and Tmin, you only have T average, then we'll need to somehow estimate what those might be on a daily basis. Then we have relative humidity. This is what I found to be the simplest thing to find, is a monthly table of relative humidity. And this is average monthly relative humidity. It turns out you can get better, more accurate simulation if you have min and max relative humidities. But those seem to me harder to obtain. So you can still estimate it, according to the document, you can still estimate it with these average relative humidities. Also, if you have dew point temperature, that would be even better according to the document. If you can get dew point temperature, you can base the calculations based on that and not relative humidity. You wouldn't need this. So you can replace it if you have that. One more thing about dew point temperature is you can use your T min as an approximation of dew point temperature as long as you're not in a very dry and windy location, according to the document. But for now, I'm just using relative humidity. So just so you know, you can do some different things here with this. The last one, it's UH. UH is just the typical variable name used in all the calculations. It's for the wind speed. Maybe I should actually call this wind speed. That's kind of, I mean, we don't need to be wind speed table. So this is monthly wind speeds for the location. Okay. Now, obviously, these variables are highly uncertain, right? All of these are. So the better you can get with your daily data is better. Right now, we're just working with monthly averages, and so our output's going to reflect that. So just keep that in mind. Okay, but those are the main inputs that we need that drive this model. So let's step back outside a little bit here. By the way, if anybody's having any trouble seeing the words that are on the screen, let me know and I can increase the size. Anyway, let's go into the model. So in the model, we take all that climate data and we put it through a bunch of calculations. But let me just talk about a few things. So on the temperature, we use both min and max and mean. So mean is easy to get if we have these two. But we also use the previous day's temperature. It's for a very minor part of the model, which also might be set to 0 anyway, so it doesn't matter too much, but it does use the previous day's temperature there. The air humidity. Now I'm drawing from a table of monthly values, and the problem when you do that kind of thing and you have a daily time step, you end up with a kind of a stair stepping of changes, between each month, which can affect the total outcome of your model. So what I like to do sometimes in these cases is when I only have monthly data is to use a spline interpolation. And so I've put one in this model, but you don't have to use it. Anyway, it's useful to just change it from a stair step because we've gone to a daily time step. It's better than linearly interpolating between values because that doesn't necessarily capture correctly the mass balance. If with spline interpolation, it can more smoothly represent the changes as we walk over all of these stair stepping monthly changes. So this spline interpolation just uses a script element to do that. It just takes the vector of 12 monthly values and converts them to a smooth daily fit. I think it'll also go to hourly fit as well. But anyway, now we have a smooth curve of mean relative humidity, and then we can calculate what's called the actual vapor pressure. And this is key for calculating ultimately evapotranspiration. But like I mentioned before, a better way is if you have dew point temperature, and I don't have it, but I've set it equal to, this should be min. I'm not using it, so. But you could set dew point temperature to min as long as, like I said, it's not too windy or dry in the area. So just be kind of careful with that one. But if you happen to have that data, great. This would be a better estimate. And what you would do is you would just swap this EA dew out with this one that's being used here. You can just swap it out. So that means you would have to find out what this is affecting. So you'd right-click Effects, and you'd have to go to these places to change the reference to this one. Okay, so that's air humidity. Now we'll talk a little bit about these atmospheric parameters. These are constants, and they are based on the location and the elevation. So they're really essentially they're modeling these constants that are just based on the Earth relative to the sun and throughout time. And so that also means, by the way, we are referring to time components in this model. And those of you new to GoldSim, you can see how GoldSim is using time components by going over here to the browser, right-clicking, click Show Element Subitems, and then expand this thing called Local Properties. We are using, in GoldSim terminology, we call them run properties. And in our case, calendar time, we're doing a calendar time model. And in here, you can see that we have these blue symbols next to the names here indicating they are in use within the model. So these are time components that are built into GoldSim that while we run the simulation, it keeps track of what these things are so that we can accurately simulate, as the model walks through time, what these parameters are. Okay, so these parameters are then driving the solar radiation calculations. So there's a lot going on in here. Essentially, what we start with, and you can look at this graphic to kind of refer to these names that are being used in the model, but essentially we just have all these components in the atmosphere as we're driving down toward the soils and plant surface, and then essentially doing a balance, an energy balance. And I just wanted to emphasize that these equations are physically based. So this method would be more suitable than if you have good data, or even if you have good estimates of the data like I was describing. This would be a better method to use than something that's empirical, like the Hammond method or the Hargreaves method for evapotranspiration, because of this. So anyway, we do this energy balance, and a couple other things I wanted to make note of. We have the components over here going into RA. This is extraterrestrial radiation. You can see in the graphic, it's the radiation coming from outer space, all just based on location on the planet where you are. But then when we go from there, we're starting to talk about, okay, we've got cloud cover and that reflects some things. Well, how do we simulate that? Well, we do that by using sunshine hours. And that's where, going back to the inputs of the model, one of the things we needed to input was the daytime sunshine hours. And so that's out of a 24-hour period, how much of that would be sunshine? And so we have just daylight hours, and that's dependent, that's N. This just depends on where you are on the planet. But then we reduce N by determining cloud cover throughout the day. So for example, in the Seattle area where I am, then our numbers would be smaller than, say, in like Phoenix or in a desert area. So in the sunshine container here, I'm doing a similar thing. I've got an input table of monthly stair-stepping values, and I'm just smoothing those out by saying we have a smooth curve for a daily model. But still, those would be average. And in reality, those numbers are going to be bouncing around with some uncertainty in there. Okay, so from that point, we're able to capture the remaining parts of this energy balance, and we end up with this Rn, which is the main, Rn is the main driver of evapotranspiration. Now, I was mentioning earlier the effective soil depth and also the previous value of the temperature, and that plays a part here in this thing called soil heat flux. And this is what I was talking about, how sometimes this is set to 0. In fact, the document even says, for a daily time, for larger time step, like a daily time step or a monthly time step, perhaps just set this to 0. It is small anyway, but it's really representing the flux of heat that's coming and going and being stored, within the system and then leaving. And so, and when I say, sorry, I said system, but leaving the soil. But it can hold some energy, and then the next day maybe it's cooler and it releases some, and then the next day it's hotter, so it's absorbing energy. So it's that kind of a process, but it is a small number. Okay, so then we go all the way up to where we then do the Penman-Monteith equation. So when we go in here, I've just pasted an image from the document of the equation. This is the equation. Now, I've repeated all of these input parameters because they are, this is a unitless equation right here. And because of that, I just want to make sure that I have all these units exactly correct. And so I've cast the units off. And to do that in GoldSim, you use the vertical bar. That's the key above the enter key. Use vertical bars and then put the correct unit that you need in the equation. So you should see down here where we say U2 for wind speed. Notice it says M S -1. That's the same thing as M over S, meters per second. So just I'm making sure that each of these components that I've cast off the unit at the correct unit that it's supposed to be in our equation. Okay, so we essentially do that equation right here in ETo. See, there's the same equation right there. And then because it's unitless, then I add at the end, I cast the units back on, and you do that by just putting millimeters per day. Note, if you do this kind of thing, then the entire equation must be encapsulated within parentheses in order to do that, just to make sure that it's applied to the whole thing. And then that's it. Then we've calculated ETo, and so let me just show you some of the components as we do this model. So if we're looking at solar radiation, then we see the curve looks like this, just a smooth curve. So it's just using some geometry. So you can see here, arc, cosine, tangent, etc. And as those variables change through time, then we are able to capture the curve accurately. And then from that curve, then we start adding in the other physical components of our system that we're looking at, you know, wind speed and some other things. But once temperature comes into play, then we start, over here. Once temperature comes into play, then we start seeing the numbers bouncing around because we have daily temperature values from our time series, daily measured temperature. And that is the only thing in our model right now that's causing these day-to-day fluctuations. Otherwise, we would have smooth curves everywhere. Okay, so that's the model. And now what I'm going to do is shift gears over to a demonstration where I've incorporated daily data. And like I said, just let me know if you have any questions. But I will be posting this recording and also this model. Okay, so here's the same model, but what I've done is, first of all, I set this model up to run Monte Carlo, 100 realizations. So we have randomness now in the model. And instead of relying on temperature time series, I will be simulating temperature. And you'll see right here, I have this container called TempGen. So this is a model that's posted on our website that essentially is derived from the WGen model. It's just the one component for modeling temperature. And in here, we have a stochastic element. That's where we're deriving the uncertainty from on the daily basis. And this, I can correlate temperature to other factors. So let's say we have a little bit of temperature and wind data, and we are able to do a regression analysis and find there's some sort of correlation statistically between those two, then we can incorporate that same type of correlation into our model, even though we're generating random numbers. So I could go into my wind model, and in this particular wind model, all I'm doing is just saying it's a log normal distribution. But I can go in and I can say I've correlated it to the temperature stochastic with a correlation factor that we can then play with. And right now I'm just saying there's a 0.5 statistical correlation factor between wind and temperature. Also, precipitation does also play a role in the temperature. So I'm also modeling precipitation for that reason. Now you can see that there is an impact of precip going over here to the met data. And that's really only because we have a rainfall component. It's not used for reference evapotranspiration, which you might be wondering, well, why not? Why wouldn't precip play a role? Well, it's because precip comes later. Precip is it definitely impacts the overall water balance, but that's not the part that we're looking at when we're calculating reference ET. Okay, so really we're only, in this model, precip is only impacting temperature, just because that's the way that this temperature model works. It is impacted on a rainy day. The temperature is impacted a little bit. Okay, so next is, let's see, we have sunshine and relative humidity. Those are the two remaining items that I'm wanting to apply some uncertainty to. So what I'm doing there is, let's say for solar radiation, what I'm doing here is I'm just adding another stochastic. In this case, it's another log normal, but I'm also correlating the sunshine hours to temperature. And so my reasoning for that is not anything other than I'm just saying that I believe that there would be a correlation. I haven't actually looked at the data, but I believe that there would be a correlation between having greater sunshine duration and a greater temperature versus a lower temperature, let's say during summer months, for example. So I put a correlation factor of 0.8 here, but that would be something you'd want to consider if you were incorporating uncertainty into your model. Okay, so there's that, and then also the relative humidity. So let's go to the relative humidity. And in a similar way, I'm correlating relative humidity to temperature again, but I'm doing it the opposite because typically the relative humidity is higher in the colder months. And so I've got a negative correlation there. But that's, once again, something that you'd want to consider there. And it's just a way for me to add the uncertainty that I'm looking for across the board for all of the input parameters. So what is my basis for all of that? Well, if we go back to the input parameters, so the temperature generator is based completely on historic data. So I should probably go back. The precip gen and temp gen, you can develop the input parameters for these models quite well by using historical time series, and then you feed that into a parameter generator, and it generates these parameters that are based on historical records. So these models can represent well the site-specific data by using incorporating randomness into your model. So what we're left with then is the humidity, the wind, and the sunshine. So currently I have those three things tied to temperature. But that is something that I've kind of gone out on a limb a little bit on with those, but definitely something that could be looked at in the future, perhaps comparing those three variables with temperature would be a good idea. Okay, but with all of that being done, temperature really is the main driver, by the way. So it's good that we can base that on historical data. All right, so with that being done, let's run the model for 100 realizations and see the impact. So I'm going into here to where we look at ETO here and plotting it. So now you can see if I do a probabilities plot, right? So that's similar to all realizations. Those are all the realizations. And we can look at one realization at a time and flip through them. But essentially the probabilities is what we're looking at. This is the range of possibility of ETO over the course of a year. Then on top of that, we can start looking at crop specific, or maybe for your lake, or maybe for your watershed. But in this case, I'm just doing it for hypothetical 3 different crops. And in my case, I have crops alfalfa, orchard, and wheat there. And so I have KC values for initial mid, and end. And then I have average planting day and average durations for each of the growing periods. And this is a model also on our website, by the way, for looking at crop coefficients. And this I mentioned in another article how we can really make good use of GoldSim's conditional containers to apply stochastic and randomness to our durations, our planting and growing durations. And that ability to have these conditional containers makes it for a very robust model that does quite well under uncertainty. Originally, this was built with nested if statements, and sometimes the logic would break depending on if the duration of one stage kind of was too long and went into another stage. It would cause problems. So by using conditional containers, we're able to allow for this sequential stepping of processes. What I mean by that is each of these containers will wait and not activate until the previous one is completed. And so you could have a random duration on the first one, and it will then send a signal when it's completed to the next one, which would then start that one up and continue forward through time. So it's a really straightforward and I think robust way to handle the uncertainty around the durations and planting times. Okay, so with that, then we have both the uncertainty of the reference ET, and then we also have the uncertainty of the timing of the growth periods for the specific crop types. So we can look at these for each, flip through them. We can look at statistics to see, statistically, this is the average of each of these crop types over time. And we can look at one at a time and see how they change. Okay, so, and you might be wondering, why do they drop off so sharp? And this is representative of harvesting time. When you go to harvest, then the irrigation completely stops and we're not really caring anymore about what the water demand would be, even though there would be something still going on. But in the sense of irrigation demands, they're not worried about that number. But you can see the dashed line in the background. This is the reference ET still there through time, but all being impacted by the uncertainty of the inputs that we put into it. Okay, so that's essentially everything I wanted to show you, and I think it would be quite useful for any type of water balance model that might include both irrigated crops and also a the natural plant life within a natural watershed that's unmanaged. Either one, I think this method would be quite useful for that purpose. All right, so that's the end of the presentation. I'll wait around here for a bit to answer any questions that you might have. But otherwise, thank you very much for joining, and we hope to see you next month. Okay, somebody asked a good question. How would you adapt this model to bare soil conditions? Let's pull up the document and go to table 12. I wonder if I can just do table. Oh, here we go. So table 12. Somewhere. I think it's like in an appendix or, oh, here we go. So I thought I saw something like that in here. You have to go to the bottom. They start with crops and then you go down here. Well, we have wetlands. Well, that's a good question, and I don't know the answer to it. But I would imagine that if it's just bare soil and it's pretty dry, that you might not have a lot of ET, actually. I wonder. Well, I guess you would have evaporation, obviously, but we wouldn't really have evapotranspiration. There'd be no transpiration component. So, interesting question. I don't have immediately the answer to that, but something that might be considered as looking at maybe this method is overkill, you know, when you have bare soil. All right, thanks for joining, and make sure to check our forum, both on LinkedIn and on our website, our community forum, for updates on when I post the video recording and the model examples. All right, have a good day. Bye.